Good morning. We'll get started in a minute. Okay, so let's get started. Good morning. Today we are going to finish the lecture on the review of linear algebra, and we are also going to start our material for the class in terms of operation research. So today we're going to have our first lecture on how to formulate linear programming models, operation research models. And as I mentioned in the first lecture, we have different type of operation research models within optimization. So we're going to start with the linear programming models, and yeah, I think that will be we'll stop after we formulate the model. We explain the different components of each model, and we also try to solve or formulate a model by ourselves. So you see more about that in a minute. But let's get started with we're stopped here with the determinants. So Monday we talk about different things. We talk about the inverse, the identity matrix. We also discuss how to solve problems using the Gauss-Jordan method. We also talk about the importance of getting the inverse of a matrix and how can that be used to solve a system of linear equations. We talk about the difference between linear dependence and independence, and the last topic for the review is the determinants. So the determinants are associated with any square matrix A. It's a number called the determinant of A, which is often abbreviated with D or DETA, or with this symbol. So here we have an example of a 2x2 matrix, and we have 4 elements in here. Their names are based on the location in the matrix, so 1, 1 for the first element and so on. So within this matrix, we can form different, or we can obtain different matrices. So for example, for a 1x1 matrix, the determinant of A will be the value of that element A11. But for a 2x2 matrix, the determinant of A is going to be equal to the multiplication of that element A11 by A22, so these two, And then that's subtracted by the multiplication of A21 by A12, which are these two elements. So for example, if we have a matrix like the one shown at the bottom of this slide, determinant for this matrix 2, 4, 3, 5, we will proceed as the formula that is presented above that, right? So we will look at the multiplication of A11 times A22 minus A21 times A12. So that would look like this. You have 2 times 5 minus 3 times 4. And a determinant for this case will be equal to minus 2. I know you're familiar with this. If you're taking some of those engineering basic courses, for example, statics of engineering or dynamics of engineering, you will have to be, you have used the determinants for some of those computations. So if A matrix is an m by m matrix, then for any values of I and j, the ij minor of A is going to be written as Aij, is the m minus 1 times m minus 1 submatrix of A, which is the original matrix. And it's obtained by deleting row I and column j of A. So, for example, if we have matrix A here, which is a 3 by 3, and you want to find the minor of A, in this case, the minor of A is going to be named A12. So we are going to delete column 1 and row 2. I'm sorry, row 1 and column 2 from the original matrix, and we will obtain that minor, which is 4, 6, 7, 9. Same thing for A32. We will delete that row number 3 and column number 2, and we will obtain this minor A32. Very simple. So we name those minors based on the row and the column that we are deleting from the original matrix. Why is that important? Because we are going to use that to compute the determinants for a 3 by 3 matrix. So if we have a matrix that is like this, and A be any m by m matrix, we may write A as this. So this is the notation that we've been using from the beginning. So to compute the determinant of this matrix, we pick any value of I. I is the number of rows from I1 to m. And the determinant for A is going to be given by this operation or this equation right here. So essentially what you're seeing is every time you have a pair or you have a even number, here you're going to be multiplying by -1. If you have an odd number, then you're going to be multiplying by a positive number. So you're going to look at the summation and the subtraction of those multiplications based on the row that you're looking at that point. So the above formula is called the expansion of the determinant A by the cofactors of row I. How does that look with an example? So if you're asked to find the determinant A given a matrix, which is looks like this one, the determinant is expanded by using row 1 cofactors. Row 2 or row 3 could be used, and you will get similar results. It doesn't matter which row you work with. Notice that using row 1, in which we have A11 equals 1, A12 equals 2, and A13 equals 3. And we obtain the minus of matrix A as follows. So we have A11, we are going to delete row 1 and column 1. So the determinant would be this submatrix. I'm sorry, the minor would be that submatrix. If we delete 1, 2, we are going to delete this row and this column, and the new mate or the minor will be this matrix with these two small columns. And same thing with 1, 3, we delete row 3 and column 3. The determinant or the minor for the determinant will be that little matrix right there. So using this information, we can compute the determinant using the equation from the previous slide. So this is going to look like this for A11. We're going to look at this minor. So we will have 5 times 9 minus 8 times 6. So this will be 5 times 9 minus 8 times 6. And that will be minus 3. If we look at the second minor matrix, this will be 4 times 9 minus 7 times 6. So 4 times 9 minus 7 times 6. And this is equal to minus 6. And then we have the final minor. We have 4 times 8 minus 7 times 5. So 4 times 8 minus 7 times 5. And that's equal to minus 3. So the final result for the determinant, again, now you are going to look at whether you are subtracting or adding those values. So for the first one, we are using row 1. So we are using row 1 for all of them. So this will be I plus or 1 plus 1. So that will be positive time minus 3. The value, I'm sorry, 1 times the value of A11 times the determinant of A11 plus, this is gonna be negative minus 1 times A12, which is 2, times the determinant minus 6 plus, it's gonna be positive 1 times 3 times minus 3. And the result for this operation is gonna be 0. So note that determinant of A equals 0 makes sense since the set of rows vectors forming matrix A are clearly linearly dependent. Okay, so when we have linearly dependent vectors for the row vectors, the determinant of the matrix should be equal to 0. And that would be the last slide for this lecture and the last concept that we wanted to review before we get into the material for the class. So these are the topics that we cover in this lecture. And you have your first assignment already in Canvas. So that first assignment is going to be based on the material that we cover in this first lecture. Any questions? Yes. Yeah, so you will have to expand this equation based on the number of rows that you will have for the matrix. So this will go up to m rows. So that means that as many as you need. So you will have to expand this with that equation based on the number of rows that you have for your matrix. Yeah, I'm sorry, I missed that question. So the question is, if it is not square matrix, yeah, you will not be able to find the determinant, right? Good question, thank you. Any other question? Good. So now let's transition to the next topic. Okay, so the title of this lecture is Graphical Solution to Linear Programming Problems. So we are going to start by formulating the most basic type of linear programming models in this lecture. Those are linear programming models that have only two decision variables. What that means is that you are only making two decisions in that problem, or you're looking for two unknowns. You're trying to solve for two unknowns in this problem. These are problems that are, I mean, easy to solve because you can draw the constraints in a two-dimensional space, meaning that it's easy to manipulate. You can draw, let's say, an x1, x2, or xy axes. You can draw the constraints, you can draw the objective function, and you can find the optimal solution based on that draw. That will not be the case if you get to a problem that have 3 decision variables, 4 decision variables, or an unlimited number of decision variables. So we're going to start with the basic, with the most easy to manipulate case, which is the 2 decision variable problem. We are going to solve that problem using the graphical method, and I'm going to show you how that's done in this first part of the lecture. So the agenda for today, first we are going to answer this question: what is a linear programming problem? As I mentioned, within operation research, we have a deterministic operation research model, we have the stochastic operation research models, or optimization problems, and then in this class we're going to be looking at the deterministic, and within the deterministic optimization or operation research models, we have linear programming, integer programming, and nonlinear programming, and so on. So we're going to start with linear programming. Linear programming have decision variables that are continuous, meaning that they can assume fractional values, and those are easier to solve when we compare to problems like integer programming. So you will understand this as we move forward into the semester. So we're going to start with linear programming. So we're going to answer this question: what is a linear programming problem? And first, we're going to look at what is the feasible region, meaning that space in which you're going to find the solution for the problem, and what is the optimal solution. So using all the options, how do you know which one is the best? That's your optimal solution. And we're going to solve the problems using the graphical solution of 2 variable LP problems. And then we're going to talk about the special cases in which you have alternative or multiple optimal solutions, an infeasible solution or no solution, or an unbound solution for a linear programming problem. So the learning objectives describe the general characteristics shared by all linear programming problems and learn how to solve graphically those linear programming problems that involve only 2 variables. Okay, so let's start by answering this question: what is a linear programming problem? And I like to start with this simple problem. It's a production problem. Essentially, what you have is you're trying to plan how many products you should produce per time. So in this case, we have a manufacturer of wooden soldiers and trains, and we have each for each type of product, we have some information For the first one, we have the price, or we sell the product for the soldiers for $27, but that product uses $10 worth of raw materials. In addition to that, we know there's a labor cost associated with building that product. So that product increases Yapeto variable labor overhead cost by $14 and requires 2 hours of finishing labor and requires 1 hour of carpentry labor. So that's for the soldiers. For the train product, we sell those for $21, but those use $9 worth of raw materials. That increases Yapeto's variable labor overhead cost by $10 and requires 1 hour of finishing labor and 1 hour of carpentry labor. So as you can see, there are many factors associated with each product. They have different prices. So for one, you can sell for $27, for the other one, $21. But at the same time, one of them is more expensive in terms of the raw materials and also in terms of the labor that you have to use to manufacture those. It also has 2 hours of finishing labor, where the other one has only 1. So the question is, based on this information, we also have additional information. Each week, Yapeto can obtain all the needed raw materials, so that's not a constraint. We can get all that raw material without problem, but we have some limitations in terms of the number of hours that we have for finishing and the number of hours that we have for carpentry. We also know that the demand for the trains is unlimited, but for the soldiers, at most 40 are both each week. So using all this information, we want to maximize the weekly profit. We want to make decisions that are going to maximize the weekly profit. The profit is defined by the revenues minus the expenses. So we want to formulate a mathematical model for this equation that can be used to maximize the weekly profit. So now the idea is you have all these factors, you have all this information, and you want to build a model that will tell you how many you should build per product for next week. And the answer to that was going to be based on the revenue minus the expenses, or the profit that you're going to make for that week. So to build that model, the Yapeto solution model incorporates the characteristics shared by all linear programming problems. First, you're going to have some decision variables. In this case, we have to start with that. Every time you formulate a linear programming problem or model, you have to start by describing what are the decisions that you have to make. So first step, you have to list the decision variables. So in this case, do you know what the decisions are? That's a question. So if you were the modeler, what are the decisions that you need to make for this problem? Yes, correct. So those are your 2 decisions. And I'm going to model those as my decision variables. Decision variables are typically represented by variable X. So that's why you will see every time I define a decision variable, I'm going to use X to represent that. So in this case, we have 2. I'm going to name them based on an index I. So I have a set I with 2 members, 1 and 2. So in this case, I equals 1 is going to represent the soldiers, and I equals 2 is going to represent the trains. Okay, so that's why I have X1 and X2.
So what is I? What is X?
X is representing the decision. So at the end, when you solve the problem, X is going to have a value, a numerical value. It's going to see, okay, X is the number of soldiers that you will manufacture for next week, and that will be equal to 50. I don't know that value from the beginning. That's the value that I want to obtain after solving the problem.
And for the time, that like something about be spent?
So for the time, what we are, in this case, that time is giving you a limitation in terms of the resource that you have available. And that's going to be a constraint. And you will see how that looks in the model in a minute. So you're referring to this time, or are you talking about something else? Yeah. So yeah, so what this is telling you is you only have 100 hours available for the week. So if you have to use those, you're going to assign them to trains or to soldiers, okay? So how many of those are going to be assigned to each product? Same thing for the carpentry hours. So that's your resource capacity. Those are the capacities that you have available. So let's define those decision variables. So we have X1 is the number of soldiers produced each week. And X2 is the number of trains produced each week. So when I define this as an index, what I'm saying is I'm going to define my decision variables like this. I will have Xi. Xi is the number of product I produced each week. Okay, so in that case, I don't have to use, let's say I have 20 different products. So if I were to use a letter for each one of those products, I would have to use almost the whole alphabet to represent those. So instead of using a different letter for each product, I'm using the same letter, but I'm assigning an index to the decision variable. So I can use the same letter and I can differentiate between products by the index. So Xi, when I equals 1, is representing the soldiers. Xi, when I equals 2, is representing the trains. And that way I keep using X. If I add more products, I just increase the index. But all my decisions in terms of number of products that are going to be produced for next week are modeled with X. Okay? So number of soldiers produced each week, number of trains produced each week, X1 and X2. So every time you're modeling or you are formulating a linear programming model, you have to start by defining the decisions. What are the decisions that you are trying to make with this model? Okay, so your decisions are going to, or these decision variables are the ones that you're going to use to build the rest of the model. Okay, so based on this, I can now formulate the objective function, which is the second step. So the objective function in any linear programming model, the decision maker wants to maximize usually the revenue or profit, or minimize usually the cost. So you're gonna define an objective function, which is going to be a linear equation that is going to guide your decision based on what you want to get from the solution. So if your objective is to maximize the profit, your objective function is going to be defined in that way. If your objective is to minimize the cost, your objective function is going to be defined in that way, or that equation is going to be represented in that way. Sum function, which is a sum function, it is a function of the decision variable, which I already mentioned. So this function to maximize or minimize is called the objective function. So you will state, you always have to state when you're defining the objective function if you're maximizing or minimizing. And you will see that why that is important. So in this case, we are trying to maximize the profit. Okay, so that's what we are going to define next. Can I move to the next slide? Good. You're good? Okay, so let's go to the next slide. So defining the objective function, Beto's weekly profit can be expressed in terms of the decision variables x1 and x2. So the weekly profit is going to be equal to the weekly revenue minus the weekly raw material cost minus the weekly variable cost, right? So you are getting, you're basically taking the profit that you're making, that's the price of the product, times the number of units that you're selling, and then you're subtracting the number of raw material costs that you're using to produce those, and also the cost of building those units. So the weekly revenue in terms of our problem, if you remember, we can sell soldiers for $27 and we can sell the trains for $21. So we're going to start with that. So the weekly revenue is $27 for every unit that you built of soldiers. So the number of units is a decision variable. I don't know how many units I'm going to build. That's what the model is going to tell me after I solve the model. But I'm going to multiply that by x1, which is representing the number of units. At this point, that's an unknown. I don't know what that is, but I'm modeling that with a decision variable. If I end up building 10 units, then that's going to be $270, right? But I don't know yet. And then the profit is $21 for each train, which is modeled with X2. Okay, so that will be my revenue. The weekly raw material cost, again, that is associated to the number of units that I'm producing for the soldiers. So it's $10 per soldier, and it's $9 per train. And finally, the variable cost or the labor cost is $14 for each soldier, and it's $10 for each train. Yes.
So why do we call labor cost as the variable cost?
I think that's the way we define it here. Let me go back.
Yeah, why is variable labor cost? What is it?
Variable labor cost, overhead cost. So it's going to change according to the number of units that you end up producing. So it's associated to each unit. That's what we call it. It's variable. It's associated to the decision variable. It is.
So is it like if you do more units, the labor cost will increase? Or?
With each unit that you manufacture, you're going to increase the labor cost by that amount. So if you produce one, your labor cost, if you produce one train, you're going to increase your labor cost by $10. If you produce two trains, you're going to increase that labor cost by $20 because it's associated with the number of products that you're producing per type.
And how about we have two laborers?
We have, yes. So this is telling you how much you need per product to produce one unit.
So we need 1 hour of finishing cost, finishing labor, and 1 hour of carpentry.
So
for 1 unit.
We need, for 1 unit, we require 1 hour of finishing labor. And for 1 unit, we require 1 hour of carpentry labor.
So it would be 2 hours.
It will be 2 hours total if you combine both operations.
So it will be $20 labor.
So that's the thing. This cost right here is not defined by time. It's defined by unit. I see where the
No,
confusion
but
is,
you're talking
right?
about 2 hours for 1 unit, so it's 2 hours. Like,
It's 2 hours labor, but the cost is not defined in terms of hours. The cost is defined in terms of units.
And
Okay.
the cost is $19.
so
This is in terms of materials. Yes, so if you look at the overall cost of producing the part, it's gonna be $19. Is that what you're referring to?
With the 2 hours.
With the 2 hours already included into the representation. Yes,
okay.
yes. But I see where the confusion is, because typically you will define the labor cost in terms of hours. That's not the case here. We are defining the labor cost in terms of the units that you're producing. So in summary, if we produce 1 unit of a train, that will increase your labor cost by $10, independently of if it takes 2 hours or 3 hours in this case. So for 3 hours, the overall labor cost is increased by $14 for that product. Okay? Okay? So up to this point, the weekly profit. Okay? So now that we have this information, we want to define the overall function for the objective function. In this case, we are going to combine the weekly revenue, and we're going to subtract that by the weekly raw material cost, and also subtract the weekly variable cost. So that expression is going to look like this. So you have 27x1 plus 21x2 minus 10x1 plus 9x2 minus 14x1 plus 10x2. And if we solve this, you can subtract 27, 27 minus 10 minus 14. That is going to be 3x1 plus 21 minus 9 minus 10, that is 2x2. So the weekly profit in terms of product 1 and product 2, you're going to make a profit of $3 every time you you decide to produce X amount of soldiers, and you are going to make $2 if you produce or if you end up selling trains. Okay, so you see the difference, right? And if you were looking only at this function, it's easy for you to make a decision. I mean, one of the products gives you more profit, right? But that's not the only thing that you have to take into account, because again, you have a resource limitation in terms of the number of hours that you have for each product. And also you have a limitation in the demand for one of the products, which we described in the previous slide. You have up to 40 for one of the products. Any questions? Good. So the Yapeta objective is to choose x1 and x2 to maximize this function, 3x1 plus 2x2. We use the variable z to denote the objective function value of any LP. So in this case, the Yapeta objective function is going to be to maximize 3x1 plus 2x2. So z is going to represent the value of the objective function, and we want to maximize that value. Maximize will be abbreviated by max and minimize by min. That's a common notation or common abbreviation if you use any of the software packages that are designed to solve linear programming models. When you code the model, you will type max or min because it's adopted already by the industry. So if you see max, you're maximizing. If you're min, you're minimizing. What is a linear programming problem again? As x1 and x2 increase, the objective function grows larger, right? That makes sense. For Yapeto, the values of x1 and x2 are limited by the following three restrictions, often called constraints. So constraint number one is each week, no more than 100 hours of finishing time may be used. Constraint number two, each week, no more than 80 hours of carpentry time may be used. And because of limited demand, at most 40 soldiers should be produced for this problem per week. So these three constraints can be expressed mathematically by the following equations. So going back to the representation of each product by their decision variables, we look at the finishing time. We know that for soldiers, we require 2 hours, and we're going to multiply that by the decision variable x1, which represent the soldiers, plus 1 hour times x2 for the trains. And that's again for the finishing time. And we have only 100 hours. So the summation of those two has to be less than or equal to the amount of time that we have available. In this case, 100 hours. We're going to proceed with the same logic for the second constraint. So for soldiers, we require 1 hour. So 1 times x1. And for trains, also 1 hour. And that has to be less than or equal to 80. And the third constraint, since we have a limitation in the demand only for the soldiers, we are going to use the decision variable representing the number of units that we are going to produce for soldiers, which is x1 in this case. That has to be less than or equal to 40. And those are the three constraints. Actually, we have to define another constraint, but that is a common constraint for all models. We want our decision variables always to be positive. In this case, every time that we have a production scheduling problem, we want to make our decision variables positive because you don't want to end up producing negative values. So what that means is you want to make x1 and x2 greater or equal to 0. So the minimum value that those variables are going to assume is 0. Okay, so the coefficients of the constraints are often called the technological coefficients. So what that means is these coefficients 2, 1, 1, 1, in this case 1. Those coefficients are often called the technological coefficients. And the number on the right-hand side of the constraints is called the constraint right-hand side, or RHS. The sign restrictions. To complete the formulation of a linear programming problem, the following questions must be answered for each decision variable. Can the decision variable only assume non-negative values, or is the decision variable allowed to assume both positive and negative values? So as I mentioned already, for a production scheduling problem, you want to make sure that you don't end up producing negative values. So, because that will not make sense. So you will basically make sure that those decision variables are positive or greater or equal to 0. If the decision variable can assume only non-negative values, the sign restriction will be xi greater or equal to 0, and that is added to the model. If the variable can assume both positive and negative values, the decision variables xi is unrestricted in sign. And we will see one example for that later this semester. Those are not very common, but there could be cases in which you will want to have an unrestricted decision variable. So combining the sign restrictions x1 greater or equal to 0, x2 greater or equal to 0, with the objective function and constraints yields the following optimization model. Maximization of this function subject to these constraints. So if you follow the process, what we did in class was we started with defining the decision variables. Using the decision variables, we define the objective function, maximization or minimization. And then using that information, we define the constraints. And that completes your model. So this is the first model, linear programming model, that we define as part of this class. So the question now is, how do you solve this, right? And we will talk about that in the next lecture. For now, we have to give you a little bit more information about linear programming problems. So concepts of linear functions and linear inequality. So remember, we started this class with the discussion of linear algebra. So if you see this model, you see that those equations are all linear, right? So you have a coefficient and you have a decision variable. It's not a square variable. It's not a to the power of 3 or to the power of 4. So all of those are linear equations. And the type of models that we are going to build and we're going to solve in this class are of this type. You will see linear equations for all the objective function and for the constraints. So a linear function is a function f of x of x1, x2 up to xn. It's a linear function if and only if for some set of constants, c1 up to cn, the function of x1 up to xn is equal to those coefficients multiplied by x, the summation of that. Okay, so it's the multiplication of z1 up to cn by x1 and the summation of those coefficients times the decision variables. So if you look at this format, c1 x1 plus c2 x2, that's the similar format that you see in the decision on the constraints and the objective function that we defined for our first model. So for example, 2x1 plus x2 is a linear function of x1 and x2, but this function x1 and x2, which has a multiplication of a square x1 times x2, is not a linear function of x1 and x2. If you plot this function, you will see this is a line. If you plot this function, this is not going to be a line. This is going to be a convex figure. So for a linear function, f x1, x2 up to xn, and any number b, the inequalities f of x up to xn less than or equal to b, and the function of x up to xn greater or equal to b are also linear inequalities. Still linear functions. A linear programming problem, LP, is an optimization problem for which we do the following. We attempt to maximize or minimize a linear function called the objective function of the decision variables. And the values of the decision variables must satisfy a set of constraints. Each constraint must be a linear equation or inequality. A sign restriction is associated with each variable. For each variable xi, the sign restriction specifies either that xi must be non-negative or greater or equal to 0, or may be unrestricted in sign. Okay, so a little bit more about this type of models. The proportionality and additive assumptions. The fact that the objective function for an LP must be a linear function of decision variables has two implications. First, the contribution of the objective function from each decision variable is proportional to the value of the decision variable. For example, the contribution to the objective function for full soldiers is exactly 4 times the contribution of 1 soldier. Okay, so that's one of the assumptions. The contribution to the objective function for any variable is independent of the other decision variables. So for example, no matter what the value of x2, is the manufacturer of X1 soldiers will always contribute 3 times X1 dollars to the objective function. And that's not going to change independently of what the other product will contribute. The fact that each LP constraint must be a linear inequality or linear equation has 2 implications. The contribution of each variable to the left-hand side of each constraint is proportional to the value of the variable. For example, it takes exactly 3 times as many finishing hours to manufacture 3 soldiers as it does for 1 soldier. The contribution of a variable to the left-hand side of each constraint is independent of the value of the variable. So for example, no matter what the value of X1, the manufacturer of X2 trains uses X2 finishing hours and X2 carpentry hours. Okay, so product 2 is independent of product 1. They're not connected. The divisibility assumption. This assumption requires that each decision variable be permitted to assume fractional values. And that's one of the characteristics of linear programming problems. And that creates some problems, okay? Why? Because if you are solving a production scheduling problem and you end up recommending producing 3.5 parts, that is not a number that you can use to make decisions. That is a fractional number. So you don't know whether to go with 3 or with 4, right? So what would be the right number? So the example, this assumption implies it is acceptable to produce a fractional number of trains. The Iapeto LP does not satisfy the divisibility assumption since a fractional soldier or train cannot be produced. The use of integer programming methods necessary to address the solution to this problem will be discussed later in this course. So we have methods to avoid those issues, but we have to start with the basic, which are the linear programming models. So we will learn integer programming later in this semester, and that type of model will allow you to make decisions that gives you integer numbers as part of your solution. The certainty assumption is that each parameter, objective function coefficients, the right-hand side, and the technological coefficients are known with certainty. So we know those numbers, and we assume that those are correct. So the solution is going to be based on those numbers. Feasible region and optimal solution. The feasible region of an LP is the set of all points satisfying all the LP constraints and sign restrictions. So for example, X1 equals 40 and X2 equals 20 is in the feasible region since they satisfy all the constraints. What that means is if you input 40 in every X1 and you input 20 in each X2, all these constraints are going to be satisfied, meaning that 2 times 40 plus 20 is going to be less than or equal to 100. 40 plus 20 is going to be less than or equal to 80. 40 is less than or equal to 40, and both of them are greater or equal to 0. So we call that a feasible solution because it satisfies every single constraint. That might not be the optimal solution, but it's a feasible solution. It's one solution that satisfies all the constraints. What we are trying to do is to find the best solution, not a feasible solution, but the best solution that will satisfy all the constraints. So if we use, for example, X1 equals 15 and X2 equals 70, that is not feasible because it's not in the feasible region because this point does not satisfy the carpentry constraint. If you substitute that into this carpentry constraint, you will see that 15 plus 70 is 85. That is greater than 80. So that is not a feasible solution. It does not satisfy all the constraints. Okay, so remember, we have, I always represent the solution space with this attempt of drawing a circle. So that's the solution space. And what we are trying to do is to cut that solution space so we can determine the area where all the constraints are satisfied. And then using that area, we can find the best solution. Once we limit the solution space to that area where all the constraints are satisfied, we can start the search for the best solution. So that x1 equals 15, x2 equals 70 point will be a point like outside that area. It is not inside the feasible region. So it will not satisfy all the constraints. That's the visual representation of what I'm trying to explain. That point x1 equals 40, x2 equals 20 will be inside this feasible region. For a maximization problem, an optimal solution is a point in the feasible region with the largest objective function value. For a minimization problem, an optimal solution is a point in the feasible region with the smallest objective value. Okay, so we are trying to maximize. We're trying to find the largest value. We're trying to minimize. We want to find the smallest value. Most of LPs have only one optimal solution. However, some LPs or linear programming models have no optimal solution or an infinite number of solutions. The optimal solution to the Yapeto's LP is x1 equals 20 and x2 equals 60. So that would be the optimal solution. In the next lecture, I'm going to show you how to find that. This solution yields an objective function value of, I have to write that down. So Z is going to be equal to 3x1 plus 2x2. So that would be 3 times 20 plus 2 times 60, which is 180. We say that x1 equals 20 and x2 equals 60 is the optimal solution. We are saying that no point in the feasible region has an objective function value or profit exceeding 180. So that will be the solution that will give you the most profit. So in terms of the lecture material, we are going to stop the discussion here. What I want you to do now is to try to formulate a linear programming model based on the description that I'm going to show you on the next slide. Yes, go ahead. Yes, go ahead. Yes, that's what I'm saying. So I'm giving you the solution right now. On the next lecture, I'm going to show you how to find that solution using the graphical method.
Can we do using the equations?
Well, yes, you can do trial and error. Is that what you're suggesting?
No, I'm not suggesting that.
Yeah. So what are you saying?
I'm asking how do we get having these equations, constraints and restrictions?
Yes.
How do you find 26?
Yes. So the answer to that question is I'm going to teach you the graphical method next lecture, in which we're going to plot all these constraints and we are going to plot the objective function. And using that information, we are going to find the solution. What I'm telling you right now is this is the solution. And we're going to find it on Wednesday. I'm going to show you how to build the space, the solution space, and how to find the solution. If you try to solve this, I mean, typically when you have a set of equations, you can solve this using the Gauss-Jordan method. The only difference now is that your solution is also influenced by the objective function. So when you apply the Gauss-Jordan method, you have a system of linear equations and you do the elementary row operations and you find the values that satisfy all the constraints. But now we have an objective function that is telling you, yeah, you know, that's the solution, but I want you to guide your solution to a specific direction. Okay, and that's going to tell you what the optimal solution is.
So I attended our lectures graphical solution
Mhm.
to other problems, but is it the most efficient way to do it, or it's just the one of the ways?
It's one way to do that. The step that follows after you learn how to use the graphical method is to solve problems that have more than two decision variables. The graphical method only applies to problems that have two decision variables. The reason we teach that is for you to get an understanding of what's going on, how the process works, and then we can go to the algorithm that will help you solve problems of any size. Okay, but we have to go through the graphical method first, so you understand what's going on, and then you can apply the algorithm.
Okay, the next thing, practice linear equations.
Yes,
I'm assuming you're gonna get like area, not gonna get exercise.
we're gonna get an area with the constraints, that's right. And then we're gonna plot the objective function, and the objective function is gonna show you the direction of improvement. And then using that objective function, we're gonna find the optimal solution.
Be like there will be like tiny
Yes, yes, yes. Obviously, there has to be a well-done graph, right, in scale. And you will see that these numbers are easy to plot. The solution is integer. The solution is in terms of values of 10. So you can easily plot that. But I see where you're going. Like if you end up having a fractional value for the optimal solution, a graphical is going to depend on how well you draw the graph, right? But you'll see that that will work. We are not going to stay in that method. The idea is for you to get an understanding of how the search process works, and then we can transition to the algorithm, which is the simplex method that you are going to learn to solve these problems, which uses some of the techniques that were part of the Gauss-Jordan method. Okay, so still have time.
So,
Yes.
sorry, so what was 180 hours, right?
180 is the profit. This is dollars.
Dollars.
Yes, because the objective function is defined in terms of dollars. Yes. So you end up producing 20 of the soldiers and 60 for the trains, and this is the profit. So for this problem, I know you have like the ones that we mentioned here. You have other solutions. Like if you substitute that into the objective function, you get an objective function value or profit that is less than 180. It's gonna be 3 times 40. 3 times 40 is 120. 2 times 20 is 40. So it's 160. So that solution, even though it satisfies the equations, is not gonna give you profit equal to 180. It's gonna give you 160. So what we are gonna learn is, I mean, out of this space, how do you find that point that is gonna give you the best solution or the best profit in this case? Remember, the decision is gonna be based on the objective function. So here we're trying to maximize our profit. If you define another objective function, the solution might change. Like if you're trying to minimize costs, you don't worry about the profit, then you will end up with another solution for that problem. Okay, you will find the combination of X1 and X2 that's going to minimize your cost. And what will be that solution? You can tell me if you think about it. If you try and only minimize costs, what would be the best solution for this problem? Not produce anything. So it's going to be 0, 0. Right? That would be the best solution for your problem. That make sense? Yeah. Okay. So let's start to formulate this again. An example. I want you to try to solve this problem. Not solve. Formulate this problem based on the description. This is a two-decision model as well. What I want you to do, at least for the time that we have, is to state the decision variables, and state the objective function. Let's see if we can do that in the next 5 minutes. If you read through this, tell me what the decision variables are and tell me what the objective function is. Can you read that from you, where you are? Or see if I can increase the size. So basically what this says is we have a company that manufactures two types of trucks, 1 and 2. Each truck must go through the painting shop and assembly shop. If the painting shop were completely devoted to painting type 1 trucks, then 800 per day could be painted. If the painting shop were completely devoted to painting type 2 trucks, then 700 per day could be painted. If the assembly shop were completely devoted to assembling trucks 1 engines, then 1,500 per day could be assembled. If the assembly shop were completely devoted to assembling truck 2 engines, then 1,200 per day could be assembled. Each type 1 truck contributes $300 profit. Each type 2 trucks contributes $500 profit. So we want to maximize, or we want to formulate a linear programming that will maximize truckbot's profit. And as we did for the first lab, I'm gonna let you try to formulate again the decision variables and the objective function. We're gonna discuss this before we leave today, and then you're gonna submit by the end of tonight. That too. Yes. So you write that your solution on a piece of paper, and then after we discuss, make sure that you upload the solution to Canvas. That applies also to the students that are watching the simulcast. So write down the solution for this and submit your solution via Canvas for lab 2. So I'm gonna give you 5 minutes to try to at least formulate the decision variables and the objective function. Could be, should be simple. If you understood the previous example, basically the same idea. The constraints are a little bit more challenging, so we can do those together. So remember, and the idea of the exercise is that you remember that every time you formulate a linear programming model, you have two lists: the decision variables, the objective function, and the constraints. Those are the 3 components. Okay, so let's talk about the decision variables. How many decision variables do you think we need? 2, right? Gonna use x1 and x2. So what's the definition for the first one? Yes, exactly. So number of trucks type 1 produced per day. And then we have number of trucks type 2 produced per day. Okay, so I understand if you put number of trucks 1, trucks 2, that doesn't give you all the information. Okay, so make sure that you define the thing clearly. Define those decision variables clearly. Okay, so the objective function, are we maximizing or minimizing? Okay, so this is clearly stating that we are maximizing. So we are going to maximize this function z that uses decision variables x1 and x2. So we are maximizing the profit, which is stated here. And it says that you make $300 for each truck of type 1 and $500 for each type of truck type 2 per day. Okay, so if you read the statement, they are giving you the requirements per station based on each type of product. So if you were going to devote the station just to this type of product, this is how many you can do. If you devote it just to this type of product, this is how many you will do. Okay, so how do we use that information? We start with the paint shop. We know that we have to use the decision variables in the constraints. The question is, how do we use them and how can we model these requirements? So if you think about each station, you don't know how many hours you're gonna have available, right? You only know that if you have 100% of this station available for this specific truck, this is how much you will produce. So that being the case, we can then state the constraint in terms of percentages, meaning that you have 100% available, and then you want to find the fractional numbers associated with each product that will meet the constraint. So the way you will go about that is for X1, let's say we are looking at the paint shop, you're going to have 100% available. I'm using 1 representing 100%. And then I'm going to associate a fractional number to X1. That fractional number is going to be based on how many trucks you can get painted if you devoted 100% of the station to that product. So that fractional number is 1/800. So if I end up producing 800 of type 1, then this constraint will be met. It's going to be 100. 1 less than or equal to 1. 100%. Right? If I just do 2, then it's going to be 2/800. That will be the fractional value. Same thing for X2. So we have X2. I think is 1/700. So the ratio that you end up doing, the summation of that ratio has to be less than that 100%. So the ratio, the summation of this fraction plus this fraction has to be less than or equal to 1. Remember, 1 is representing this 100%. because this piece right here is gonna be a fractional value, and this is gonna be a fractional value. The summation of the two has to be less than or equal to 1. 1 is representing all the capacity for that, in this case, paint shop. In the same way, we can formulate for the engine shop. We have 1 over 1500 x1 plus 1 over 1200 x2, and that has to be less than or equal to 1. And to complete the formulation, 1x1 and x2 to be greater or equal to 0. Okay. So remember to, once you finish your formulation, don't forget to upload the solution to Canvas. And as you can see, for this problem, we don't have specifications in terms of hours of resource availability like we did in the first problem, but we can still manage to find a way to formulate the model and to obtain a solution once we solve this. We can also solve this using the method that I'm going to teach you in our next lecture, the graphical method. Any questions? Yes. Or yeah.
Once you do that.
So this is for 1 day. Yes.
Right.
Yes. Because the decision variables are defined per day. Yes.
Stupid question. You say at the end you have to identify that this is the best solution, this is the feasible solution, or
Well, typically what you will do is to find the optimal solution, especially if you're trying to maximize your profit. You want to find that combination that is going to give you the best or the maximum profit for your company. But there will be cases in which you have a problem that is so big that finding that optimal solution will take you days, even months, running in a computer. Those problems, there's problems that, for example, the traveling salesman problem is very well studied. Like you have this person that have to go and deliver packages like Amazon, and you're trying to find the best route for 1,000. That could be a problem that can be, take you forever to solve. So what we end up doing for those type of problems is, since you cannot get the optimal, because it's going to take you a long time, we have ways of formulating or defining algorithms that can give you a good solution that is not, is close to the optimal, but it's good enough so you can use it in practice. So you don't have to wait for a long period. So in practice, you might end up using those strategies because finding the optimal solution would take you just so long. Yes. This is the solution. This is the formulation. And not the solution for the problem, but it is the solution for the exercise. Yes. Yes, this is what you want to upload.
Why do we put constraints that less than 4 equal to 1? If we want to maximize it, we need to 1.
Yes, that's a very good question. That's a very good question. But in some, if you make that problem very restricted by making it equal to 1, you might not find a solution that will satisfy that equal to 1. So if that solution exists, you will still find it with this limitation. But if you cannot find a combination that is equal to 1 for both of the constraints, then the problem will tell you this has no solution, because you are not able to find that combination. Again, these are fractional values. So you might find a solution that is 0.99999, still not equal to 1. So the problem will tell you this is unfeasible. Okay, good question. That's a very good question. Any other question? Nope. So I will see you on Wednesday. Don't forget to upload and don't forget about the assignment.
Just to make sure that this is something that you That's right. There is no logic.
Say that again?
Because you will just upload that.
Yeah, the formulation, yes. For lab two. For assignment one, you have problems, and those are due on Wednesday next week.
PDF for that lab doesn't let me open it or download it. If this is for business.
Okay, I'll fix that. So if the lab is not letting you open, I will fix that after the class, yes. Yes, so it's the same description that you see here.
So whenever you like have like the problem, right, you got all the constraints, and, like once you have it and you plug it into the computer, does it just go through like every feasible solution, or is there
No, so
written, like
yes,
whatchamacallit that'll like
the algorithm that we are gonna learn actually was developed for the Second World War, and is once it finds the direction of improvement, it kind of eliminate solutions that are not going to improve that solution. So it's gonna cut part of that search. Say, okay, this is the direction of improvement. Forget about the other part about the other one. Okay, so that's why we need to learn the graphical method so you can see how that works.
right, okay.
Okay.
That was my question. I was just curious. 'Cause,
Yes, those are good questions.
like obviously like sometimes like you can like bombard a computer and just let it do all the calculations because it might be a small area. But like if there's so many constraints and so many different variables
Yes.
that it's hard, and
It's like
you need a supercomputer or millions of years to figure
Yeah.
out the exact solution. That's why I
so
was curious.
total enumeration is a way of solving it, but it will take you forever.
Yeah.
So that's why these other algorithms are developed, so you don't have to go through that
Right.
process. Yeah. And even having these algorithms, and that's why research is always moving forward. We have people working on better algorithms every year, so we can get to solve problems that are unsolved right now. Yeah.
Okay. All right.
Yeah.
Thank you. You have a good day.
So you send me so I will send you a time to meet. Like you
Okay.
said that you cannot meet during my office hours, right?
I can do office hours on Wednesdays and Mondays, but I can't do Thursdays because I have.
What about Fridays? You meet on
Yeah, I
Fridays?
can do Fridays.
What time will be better for you?
So I have this.
Can you send me an email?
Yeah,
Can you
I'll
send
send
me
you.
an- Okay,
Okay.
good.
Thank you.
Professor, when are your office hours today?
No, I have office hours Tuesdays and Thursdays from 8:30 to 10:30. 8:30 to 10:30. Yes.
Any way we can schedule any appointment with you? Because I don't live here. And it's somewhere.
Yeah, so
Today,
even if I'm having office hours virtually, so we can schedule it outside those times. Just tell me what will work for you and we can schedule that.
today, anytime after.
So today is Mondays and Wednesdays I'm teaching, so my schedule is mostly occupied, but that's why I have them on Tuesday and Thursdays, and Fridays I'm very flexible on Fridays. So
I will send you email. We have off Friday. So
Yeah. yes, that would be better for me. Okay. Oh, you too.
Thank you.
Bye bye.